I would like to introduce myself. My name is Eddie Santosa. I'm with Kellison RTKL. I will be accompanied by Ian Malloy, Senior Product Manager from Autodesk. Today I would like to share about how implementing the early performance design that can help you make your building greener and higher performance. As we know, in our current industry, green building is become a mandatory almost in all projects, not only because of LEED, sometimes the local code require that one. Even now people start talking about net zero building, carbon neutral building. So one of the key to make a successful building is to implement the early performance design. And in my session, I will like to share my experience dealing with early design. And Ian Malloy will show the new product from Autodesk that just launched, I think, last week, 2 weeks ago, that can help you make your process simpler and easier. In my presentation, I will starting discuss about why we do it and how the best recommended approach to do the early performance design. And I will share 2 case studies, and Ian Malloy after that will demo the new product from Autodesk. Why we do the performance design? There is 2 options to make higher performance design. First, usually using a better product, using photovoltaics, wind turbine, or any other new product in the market. That usually comes the first when you do a design charrette. People always put a PV in my building. But as a design industry, you want to differentiate yourself. How you want to differentiate yourself? Make a better design process. That's the one that you want to sell as your main value if you're in the design industry. Design process, make a better design process in early design using the performance design definitely become a key of the success. It's just less than a month ago, AIA released a press release that showed that to achieve the carbon neutrality, the energy modeling is a key. Again, they repeat again. So when AIA start embracing the notion of the carbon neutrality, it will become a standard practice in our industry. LEED also in a latest release on a version 4, they put integrated process design as part of the requirement in the project. You can get a 1 credit if you do early performance design. What's actually the benefit to implement the early performance design? Early performance design usually dealing a lot with the architecture portion, and it typically it can reduce around 15% of your energy use. And also, it also impacts your peak load of the HVAC system. It means that if you implement early performance design, your HVAC system will have a smaller size. So you also reduce your initial cost of the building. This is a new report from AIA showing different performance between the model building and a non-model building. And you can see the model building performs about like 10 or 15% better. It's similar to what I experienced in my projects. But interestingly, the model building can perform minus in here. What happened? Is the baseline in the AIA 2030 is actually based on a survey building in 2003. So what happened in here is typically people use the wrong baseline, or they have a lack of the knowledge to implement the early performance design. So this is a key, because it doesn't make sense your building that designed in 2015 or 2014 perform worse than the building in 2003. So how to make it better? How you can measure that you do better in early performance design? So this is the process in an energy model or performance design. Usually you have early energy model, final energy model, the real energy uses of the building, as well as the calibrated energy model. We had a conference, I think last month in Atlanta, discussing about this one. So I was thinking, how about we proposing a 20-20-10 rules? It means between the early energy model and your final energy model, the difference shouldn't be more than 20%. It means if in your early design showing 30% better than energy baseline, your final in the CD level shouldn't be more than 26 to 36, 24% to 36% better than energy model. In here is why we use the 20% is also affecting your lead point. You cannot, in the 20% range, usually you get a plus minus 2 points in lead. After I show you why we do it, I will like to share how we do, what is the recommended approach that you can implement in your project. This is actually a diagram that I generated a long time ago. I think I generated 2011 when I was still with HMC Architects. This is show you how we can use early performance design and implement the different performance assessment in different stages of the design process, from pre-design, schematic design, design development, and construction. As you can see, the early performance design usually in the pre-design and schematic. And you can see different type of strategy that we can use in the building. In Callison, we develop slightly different, but fundamentally always the same. So we typically, the performance design that we do in our architecture firm is starting with established energy target to the agency and lead analysis. But in early design, we usually concern about established energy target to shading strategy only. So this is the range that we can do in the project that can help your building perform better. Since it's Autodesk University 2015, so I will talk about the software. I usually not sharing what software that I use in my project. This is a typical software that we currently use in our process. In a climate analysis, we usually use a climate consultant and DView. Both is a free software. The daylight, currently we use a DIFA for Rhino. The solar radiation, I still use Ecotech and DIFA for Rhino. And in energy analysis, primarily we use Equest. And wind analysis, this is actually Autodesk Flow. It's a nice product from Autodesk. In terms of drawing platform, we're dealing with mostly SketchUp and Rhino. And in the later stage, we're dealing more with a Revit platform. In the future approach, this is what I see that will be happen probably that we will adopt in our current process. In a climate analysis, we experiment already with a Tableau. Tableau is a data visualization. So it's not only showing the graphics, but you can navigate and hover around the number. And again, this is using a Form 8 360 Pro that you can just grab the location and get the information really quick. In the daylight, you can use Revit. I think we just tested a few times, and it's really fast compared to DIFA. And the solar radiation, we will make a combination probably between Form 8, Revit plugins, which is InSite 360, and DIFA for Rhino. In energy analysis, I think we can use Revit plugins with InSite 360, Green Building Studio, and also in the later stage, probably people starting using Open Studio and Energy Plus engine compared to DOE2 engine. Wind analysis, I don't find any other software that have a good range of the price and capability yet. In the drawing platform, if you see the Form 8 360 actually have a really good capability and that you can export also to get the performance modeling in the solar and energy analysis that you can be combined with the SketchUp, Rhino, and the later state. I think Revit is always will be the main platform. That's about the software, but the main success of the building is rely on a collaboration. In the early design, definitely you need to have collaboration between architects, mechanical engineer, lighting designer, and energy modeler. If you still design architect only in early design, most likely your building will not perform really well. So the software is one thing, but the process will be the key of the success of your project. I would like to share two case studies. The first case study is actually the competition that we did 2 months ago in Atlanta. I will be part of the Autodesk team. There's a Stephanie here that will be involved also. We actually designed a net zero building in this project. It's a 53,000 square feet building. What we do is we develop the framework before we start. We do a climate analysis and study, meshing study, and schematic design, and detail analysis in the end. This is our first climate study. We put the building in San Diego. We generate this all information with Form A360. I think with this one we get from the one of the website, government website for this one. But this one can be easily generated with Form A360 without you need to upload your weather file. This is some of the early study. Form A360 allow even mechanical engineer that doesn't have an architect background to just develop a meshing and run the performance in the building. So actually the scheme that we choose was actually developed by mechanical engineer, not by architects. And you can see you can get a energy cost budget. This is actually showing $8.64 per square meter per year, or about 80 cents per square feet per year. I think we don't put the correct unit when we develop the early one. After that, we bring the scheme that we like to Revit, and we develop the Revit model, and we do more detailed study on that one. We're still using the older plugins, not the latest one in this project. And you can see the energy cost actually slightly go up. Before it's 80 cents, and now it's become $1.50. And in the Revit, you can just pull to doing a daylight study, doing a solar radiation, and also using Autodesk Flow, you can do some of simple wind study. In here, based on the solar study, we put the shading in the building. To optimize further, we use a green building studio and do some optimization. The first optimization that we do is actually study different type of window wall ratio. 30%, 40%, 50%, and 50% in the northeast and 30% in the southwest. So we have a different performance on that one, and we choose based on the best one, 40%. And an envelope we test using the ICF wall, the mesh wall is a regular concrete, and the metal frame. And this one is not so much different, but when you go in a green building studio, there is a slightly different between the number. In the system, we actually tested more than 4, and we come out that this package heat pump system performed the best one in this case. And we also reduced the lighting power density, the number of light in the building, to 30%, which is typical approach if you have you want to achieve a net zero. At least you need to reduce 30% or even further. This is our final project, our final result. That our building consume about the dollar value, about per year, 48,000. With this is a breakdown of kilowatt and the natural gas usage. And we also have a space on the roof that we can put almost a 394 kilowatt system that can produce 71,000. So our building actually is a net zero if you're looking from energy cost budget. If you see the comparison between our early design with the final design, our early design is $8.64, which is per square meter, and it's actually around 0.8, and our final design in here is 0.94. So you can see the range is not that far. So you need to make sure when you're doing early design, keep tracking the number. So you know the assumption that you use in early design is valid, or if not, the number is too far, then you need to assess your process again. So it's not only you can do just early design as that you don't keep tracking, you cannot improve your process. You need to keep tracking and you can improve your process in early design. The second project is actually a government building in Atlanta. It's an office building, it's a renovation building. We just working in this project. This is an existing project actually. This is a existing building. And we developed the one in the between. It's like corridor, and we improve the performance, improve the envelope, and do some of new lighting and new HVAC system. We generate the weather file using climate consultant for this one. This one we're using a DView to generate different type of humidity and dry bulb temperature. So for our initial study, we use a new InSite 360. When we received that, we heard that InSite 360 coming, so we test the building that we have a Revit model, and we test that using a InSite 360. We do some rendering of interior design, and also you can do exterior rendering with that plugins. This is a energy model that we can bring to the, we can push to the InSite 360. Even in the visualization, you can do some section, you can do seeing the perspective of that one. In addition of energy modeling and performance modeling, we do some checking also in the energy code. So when you do early energy design, you have to really know what's going on behind. What is your performance target based on the current code in the state? You cannot just using the software and just click it and get a number and you don't really understand what it means. You need to have some background understanding of what is the baseline, what is the requirement in the city. So we do some parametric adjustment in InSite 360. You can make adjustment. What is lighting efficiency that you can choose in a building, and we do some adjustment that we think is suitable for the office building. Our target is not the lowest one. If the lowest one doesn't make sense, we cannot implement in the building. We don't choose it. So we choose the one that kind of makes sense in our project, and we try to see whether it can achieve the target of the project. The project actually needs to perform 30% below ASHRAE 90.1. So we try to choose the one that makes sense, that based on the cost estimation that we have also in the project. This is some of the adjustment that we make. You can see we don't always choose the most expensive one. For example, in the window glass in here, we choose a double OE. This is a standard that we currently have in the building, and we don't planning to replace it. If we go to the triple OE, I don't think we have a budget in the building. So when you use software, you need to make sure you understand the cost of the budget and also the performance that you want to achieve. So this is the performance of the building. The early one, if you just click the software, you get 104, and you make adjustment in the parameter, you can get a 47.8%. In terms of the percentage that the reduction that we use, this is the early one. If you don't make adjustment on parametric, it can be that range that happened in the building. So that's why you need to narrow down until the final one. Ian probably will show part of this one, so you probably get more understanding. This is basically, if you don't put any of the parametrics, your building performance can be that high range. So you need to narrow down each option, so you get a better narrow option in here. So this is the final performance. If you compare with ASHRAE, this is ASHRAE 2010. Our building is about 25% better, which is if you compare to ASHRAE 90.1 2007, probably we achieved the target, which is 30%. So you can see in early design, we still need to track, make sure that this number makes sense. Otherwise, if you get this number 50% saving or 5%, then this doesn't make sense anymore. So after you understand that the number makes sense, then you can start using the parametric number on information that you start giving to your electrical engineer or other engineer that they have this target, and you can start a discussion. For example, in lighting, our target is 0.7 per watt per square feet. You need to give that information before they design. Otherwise, after they finish the design, they cannot make adjustment anymore. And what type of mechanical system that makes sense with this target. And with the InSite 360, you can just click and do some of daylight simulation. I think it's a really good performance. We just tested 1 or 2 times, and really fast. Usually we do using a DIFA for Rhino. DIFA for Rhino, usually if you want to running this floor plate, it takes about 12 hours to 24 hours. This one is run really quick because in the cloud. And we also do some SunPad that we miss from Ecotech. Actually, I still like the Ecotech part. So this is, but you still have an option to do the SunPads and shading strategy in here. And you can use it for your presentation or to show your design concept in here. This is some improvement that we do after we get the result. I told the architects that probably we need to reduce the number of class in here. He's still playing of the different scheme and reducing some of the class on the option. Although I think they will need to reduce more to get the target 40% of window wall ratio. But you can see the improvement from the initial design that have a lot of class. After they get information that they need to maintain a certain window wall ratio, they need to make adjustment on design. If you do this adjustment in a construction document, it will be painful. So it's rather doing it early. So when you in the CD, you don't need to make any big change anymore because you know the performances will be there. You know the target. You will get the target if you follow the requirement. After I show you the case study, I will hand out to Ian Malloy. He will give you some of the InSite 360 product and how to use it. Go ahead, Ian.
Okay. Thanks, Eddie. So, so Eddie has been one of our early adopters and with us through a number of years as we went through technology previews on Autodesk Labs and a number of beta features and things like that. And I'm sure many of you here have followed us on that path as well. And so following a lot of that work and learning, we've managed to bring that all together and present it under the banner of InSite 360. So we're really excited about this. We launched a green build 2 weeks ago because what it kind of represents is everything that Eddie kind of shared with you there from the workflow perspective, from the problem that we're trying to solve, and also from how the tools all work together. We've done a lot of work to bring them all together and make it a much easier, much more cohesive experience for you. So what I'm going to do is I'm just going to give you an overview of it, a little bit of a demonstration of it, and you'll see how a lot of the things that Eddie was doing there actually work today, and it's all available to you. So just to explain a little bit about what it is at the very highest level. So we talk about being an outcome-driven guide to building energy environmental performance, and the reason we describe it that way is that traditionally a lot of tools are very input-orientated. You know, it demands a lot of information up front that you don't necessarily know. And then it's essentially you get a single simulation at a time and you've got to sort of run individual simulations and tweak things to sort of understand what the drivers are. And we've taken a very different approach to this, essentially turned it on its head, and I'm going to explain how we do that. But the really critical essential essence of this is that to start with, we want some very clear indicators of performance, and one that encapsulates a lot is the energy cost range. And so we've got this indicator that very clearly kind of shows you energy costs. You can also switch it to EUI if you like, but we use cost because everybody can understand it. Owners understand it, and you ask people who understands EUI, not everybody does. So it's and cost is also tangible, and it speaks to the value of making these decisions. But we want to give very clear indicators about what's good and what's bad and how you're doing. So this dial here, as it goes from red to orange, is going from actually 90.1 to so from not meeting code to code, and then you eventually get to green with Architecture 2030. But of course, having that clear indicator of performance is only as good as the parts that drive it. So we've got this interaction model now, which is entirely web-based, meaning you don't need to have Format or Revit to look at these results. But what it allows you to do is see clear cause and effect between the key factors that drive building energy use, like orientation, window-to-wall ratio, glazing, roof insulation. There's a whole range I'll go through a little bit. But very quickly see, by looking at a range of things and reducing the range, how that moves your performance. Also the ability to visualize results like heating and cooling and solar radiation in the model, and then also plot paths towards higher performing buildings, like in this case showing the series of decisions and sort of design packages that need to be taken as you go from sort of doing nothing to achieving Architecture 2030. And that's the indicator we use for good, because again it's very tangible for people. It's based on a relative improvement over building stock. But the basis of this is that as you model in Format and Revit, and as fast as you can model, we look after the model translation, the creation of an energy analytical model, and that means that you can do very quick comparison at a design option level, and then see very quickly side by side what's better, because that really is, at the end of the day, the goal of analysis. It's not about running analysis for analysis' sake, but it's about being able to do comparison and see trade-offs and understand, how you're going to get to a better performance. So just to give you an outline of the workflow and what you require to get started, the good news is that all you need to do this is to have either a subscription to Format 360 Pro or a Revit subscription. So just out of interest, how many people have Revit here? Okay, right, so you all have this, right? There's no additional charge or anything like that, and you can use it as much as you want. And basically all that we ask is that you need to set the location. That's pretty critical because it brings things like climate information into the mix and starts to, it's one of the big parameters or factors that you can set that we know quite a lot about because we have a lot of historical data that we can use. The only other thing that we actually do is just click a button called Create InSite. And what that actually does behind the scenes is, first of all, automates the creation of the energy analytical model, which many of you will probably have seen from following us in Revit that we've done a great deal of work on enhancing how that works. So basically, if you can do basic architectural modeling, you can now get a very accurate energy analytical model from that with no real special requirements on how you model a building. And then essentially what we do is we take that analytical model and we run what is essentially equivalent to millions of whole building energy simulations. We don't actually run millions of simulations because that would actually be, very wasteful. And what we've actually done is we've got a special way to parse out the overall landscape of things that drive building energy. We call them factors, run the ranges, and then combine those results with a very, so without running millions of simulations, we can still get a very good indication of what the actual combinatoric effects, with a small loss of accuracy, but it's well within the margin of error of around plus or minus 10%. But what you'll see in the way it presents the results, it completely changes your interaction with things. So from that, you just can open up InSite 360, and then you can explore energy cost range, the factors and savings. You can visualize heating and cooling, and of course, lather, rinse, repeat. We expect you to not just do this once, but do it many times throughout the design process. So from the earliest moments, you have some sense of the building massing and its context. You can start to model it. You can start to run this analysis and can continue to do it throughout the process. So I'm just going to switch over here and I'm going to sit down, if you don't mind, just so that I can operate the software. So I'm on 5. There we go. Thanks, Eddie. Okay, right, so this is InSite 360. So basically, I'll get to this in a minute, but this is the sort of the home page of it. It's kind of structured around a kind of a gallery. You can use this to kind of organize the different analysis that you run, your different design options, and you can use like one for a project or projects at different stages. It's entirely up to you how you want to organize them. But basically, again, like I mentioned, I'm in earliest stages of the design process. From the moment I have the simplest representation of the overall building mass, I can simply set my location, go over here and click Generate InSite. Equally in Revit, and I'm going to sort of expand it a little bit more because a lot of magic happens behind the scenes in Format that you can't see, but you can see it in Revit. This set of models here is just an example of going from a very early conceptual massing stage through to schematic design into detailed design. And the point is, everybody in the architectural modeling process does this differently. They have different modeling styles and modeling practices. The models include different levels of detail and small gaps and overlaps. And it's not a particularly precise process, which is what a lot of analytical model creation workflows have required in the past. So basically, the whole automatic model creation is looked after, and so what actually happens when you click that Generate InSite button is that we actually use Revit in the cloud to actually generate the energy model. And as you can see, this is the energy model which you can see in Revit, and you can see, although we started with basically a simple mass with 3 floors, you can actually see we've automatically created the perimeter and core zone, and we've divided it by orientation and so on. And that spans all the way through the design process into schematic design. So you get this really interesting phase between conceptual design and schematic where you start to place curtain walls and shading and interior layout and so on. The point is, for each additional level of articulation that you add to the physical model, each decision that you make, you can run this analysis all the way up to a very, very detailed model that contains rooms and spaces and so on, and captures the energy model at that level of detail. Naturally, the level of energy model precision and detail is relative to your building information model. So with that behind the scenes, what basically happens when we click Generate InSite, I'll just go back and show you again. What you will need for Revit at the moment is a plugin that provides all of the tools, which is Generate InSite plus heating, cooling, lighting analysis, and solar analysis. And basically, again, set the location, click Generate. And depending on the size of your model, these sort of conceptual things take about a minute or two to run. And at this detailed stage, it takes sort of 10 to 15 minutes. But you tend to do a lot of cycles early on, you do less later on, but it's very, very fast for the amount of information that it's actually providing in response. So what I'm going to do now is just jump over to InSite 360, and by default what happens, all of your analysis go into an uncategorized folder, and you can group them into a folder so you can sort of like tell a story. And what I've got here is essentially that series of Revit models that I created, all reflected here in InSite. So we have a very high level comparison. The internet connection is a little bit slow here, that's why it's just taking the time to update. But basically, what I can see here side by side is all the different design scenarios. I'm just going to pick on one for the moment to illustrate the overall interaction model. And what I'm going to do is I'm going to start with the very beginning. So when you click that, you set your location, you've got your model, you click InSite, what you get to begin with is this energy cost range that's very broad. First of all, you're in the red because you haven't done anything to actually improve the performance, and also the range is very, very wide. So what you'll see here in this benchmark is, we're not yet at 90.1. The energy cost could be as high as 48, as low as 6, and at the moment the mean is 19, and that's what this number is reflected here. Now, the other things just notice here is that in Revit, where I'm able to see the analytical model that was generated here, I can see the analytical model that was generated as well, and we can kind of take it apart to see the zoning. So just it's a good way to understand, that translation that's happened. But then as I scroll down here, what I'll see is this is what we call our list of factors. And you'll see things like lighting, efficiency, plug loads, infiltration, wall construction, glazing, orientation, window to wall ratio, and PV. And basically, we've arrived at these to basically establish, to map out the sort of the whole landscape of all the things that really drive building energy at a high level. And within each factor, we look at an entire range. So take, for example, lighting efficiency. We've got everything from 1.9 watt per square foot down to 0.3 with a number of stops along the way. And what we've actually done behind the scenes there is we've actually computed the entire combinatoric set of every single one of those individual points with all the others. It is literally millions of combinations. And we're presenting it at the moment as a range. So that now when I want to see the value of changing any one of these inputs, we get to see the outcome immediately on what that will be. So take, for example, lighting. It's a big driver in total building energy. And one of the things you quickly want to target at those early stages. So what I can do is I can very quickly show, if you just look at this number 19, that if it was an old building, very poor performing, you would see 22.5. If I drag it all the way to the right, 15.5, so $7 or so, a meter square per year. It's very significant, right? And so what it allows us to do now is to say, well, what are we targeting here? Are we going to be at code, which is around 1.1? Are we going to be sort of maybe trying a little harder than that? Or are we going to really push the envelope? Maybe we don't quite know yet. We know we're pushing a high performance building, so we're just going to leave it on a range. Again, we don't need to be bogged down by the details at this stage. We just want to work on each factor, set it to an appropriate range. And there's really two things going on here. One is to look at the individual value of each factor, and then the other is to set the overall model up. So then if I'm looking at something else, like as I model through the building, change its shape, add floors or whatever it might be, I get to see how that thing actually continues to track. And basically what I can do is as I go down through each of these factors, I can save the state of them just by creating what we call a scenario. And as you go, you get this series of scenarios built out here. So the example that I've given here is very early targeting and feasibility for how we're going to hit Architecture 2030. And what I can do is very simply just plot this graph here that shows, right, this is us starting doing nothing. This is us improving the lighting power density and equipment. This is us improving the envelope, the HVAC systems, and then finally adding photovoltaic. And again, none of this has required really much effort. It's all very conceptual, and PV is a great example. We haven't gone in and had to model a PV system. What we've simply said is, what level of PV coverage do we have on the building? And so I can see here by just changing this range here what the impact of that will be. So we can put in a percentage of roof. It doesn't have to be an actual detailed model. Later on in the process, we can add that panel in and we can simulate that and look at the actual incident solar radiation on it. But what it gives us is this very high level plan of how as a team we're going to achieve our performance factors. And then from there, you can continue through the process. So the next example that I have here is actually a window-to-wall ratio study. So previously in that last example here, the targeting, I hadn't decided window-to-wall ratio. I just knew each elevation is going to be somewhere between 30 and 80. And so we're going to see now what that looks like and how you can have a kind of conversation with an owner about the impact of glazing and so on. So what you'll see here is that, again, I've got a series of scenarios created where each of the window-to-wall ratio factors have been varied. And when I plot them, you'll see what the story that it actually tells. And this literally takes minutes to put together. So first of all, this was our conceptual target that we created earlier. And if we were to push all the window-to-wall ratio up to 80%, you'd see that we completely blow it out of the water, right? We make a major jump in energy cost. If we go to 65, you see again, it's, as you would expect, somewhere in between. If we would go to 50, we'll see we can achieve our goal. But again, if we want to really, everybody likes windows, we want more, we can achieve our goal at 65, but if we also improve the glazing. So basically, it's a very clear way of actually helping people understand what these solutions look like, and without having to run lots of simulations individually and sort of randomly explore the problem space. Other things that we can do as well that help people understand what energy simulation is, and other design decisions that again can start to be looked at from a very early design stage are heating and cooling loads. So everything you've seen so far in energy simulation is run using DOE 2.2 simulations, but we're now using Energy Plus to also do peak heating and cooling load, and we use this little model viewer to show in context what they actually mean. So if you just look at this menu here, you'll see a little cooling load symbol. And what it'll do here is it'll color code the model based on the peak heating and cooling loads that it finds. And you can kind of see, in this case here, red means hot. And basically, if I click on that space there, you'll see that particular space or zone is 205 watts per square meter. And you'll see the other parts of the building at the other elevation. This is basically an east and west elevation. So this gives us clues to things that we could do around improving the glazing on those elevations, which again allow me to go back to my Revit model, and as I start to put in curtain walling, I can start to embed the thermal properties in there and start to override those factor settings and understand the implications of those decisions. So that's essentially an overview of everything that sort of InSite 360 does. Another thing I wanted to sort of mention about it, though, is that the actual approach to it is interesting insofar as it's not just applicable to conceptual design. It can also be used for sort of preliminary and high-level analysis of existing buildings. And one of the examples that I have here is that exact same building model. Again, we could model it at different levels of detail, but what I've done here is use it to represent an existing building. And when you do these kinds of energy auditing type studies, there's a lot you don't know about the building. Like you don't know the exact wall constructions, you don't know the exact glazing. So this is where a range becomes very useful, because you're probably, if it's an old building, you're not at code, you're somewhere less than code. So you can very quickly use the factors to say, well, look, we know it's leaky, so the infiltration is in that range. We know the glazing is in this range. And what it allows you to do is, again, set an overall target and understand the role of each thing, and then similarly, again, plot a path to how you're going to get to a better place. And so again, I've just got a series of packages here that sort of outline what your path to, again, in this case, Architecture 2030 might look like. It's a little bit more challenging on an existing building because you don't have the flexibility over, you don't usually have things like window-to-wall ratio and so on, but you can do more around envelope and systems and things like that. Okay, so that's basically it. So all I wanted to do now was just flip you back over to Eddie. So if anyone has more questions about this, we're here all week, and come see us. There's more classes that we're covering this on. What I've really only shown you here is the energy side of things as well. We've got more detail on the actual solar analysis and lighting analysis, which again talk to the energy cost range. But we just wanted to give you a sort of an oversight of how all the kind of work that Eddie's been doing, and a lot of our users through, as I said, like our labs and things like that, have helped us get to this point where we have this capability that's very easy to use, and we think solves a real problem. Okay, so I'll switch you back to 8. What do you want, 8? Yeah, there we go.
Yep. Okay, after we discussed about the methodology and Ian already showed the software, so before I close this session, I would like to share probably 4 things that you probably want to pay attention in the future. The first one is a more weather file. There is, I think, a lot of discussion about how we use energy model, what kind of weather file we use. Typically, we use a weather file that 10 years ago or 20 years ago. So if you believe that the climate change probably will affect our current weather file, you probably want to start exploring the use of a future weather file by morphing the weather file on the project. We did several studies on that one, and although the peak probably different only 1 or 2 degrees Celsius, but it's quite significant different in terms of like solar radiation and other things. BIM to BPA, I think building information modeling to building performance analysis, like the one that Ian already showed, is like how can building information modeling can be transferred to BPA. Currently, there is still a process that you probably need to make adjustment on the process, and how the final energy model can be transferred to the code compliance directly. So how that information will be can be transferred easily compare what is the current process. The data visualization, I think, it's become a trend. It's not only in architecture and building industry. Everybody want to get more information about how people using a building, how we can use that information in your energy model, because sometimes we just make assumption. So if your firm doing a lot of school project, you probably want to start collecting data, how they use a building, so you can represent better information in your model. Visual and augmented reality in the building performance. I think there is in my previous University of Pennsylvania, they already playing with augmented reality on a wind study 10 years ago. I don't know the progress. But in our firm, we currently play with daylight simulation with a GearVR. So we try to use a visualization and try to use the power of VR in building performance as well. So you not only get the rendering, so you can also generate the daylight performance in the tools, and client can see the difference, not only how it looks like and how it performs as well. It also probably impact on a rendering process. I mean, currently people always using photorealistic rendering that never happen in the reality, right? It's photorealistic, but it's especially graphic artist representation. It's not a real project that you see in a building or a real project that you see in the site. So that probably will be changed in the next few years. I think if if there is any question on the process or any question for Ian on the stuff, I think we still have plenty time. So I open to the floor. Yes?
There's a chance, yeah. You know. So yeah, you know how it is, right? We can't we have this thing about what we're doing in the future. But yeah, you know, InSite provides a platform. You know, if anybody looks at just what we've done in the last year, and you know, we're continuing to push. You know, it offers us this opportunity to bring more performance information, which is typically been challenging to do and interpret into actual actionable decisions. It gives us an umbrella to sort of do that, and a vehicle to do that. So yeah, it's something we're definitely looking at, and not just that though, other areas as well.
Yeah, in my side, I think Autodesk Flow is a pretty useful tools, and we use a standalone one, less stress and less problem. If you have a big model, typically the flow is currently a little bit having difficulty if you have a really huge master plan, for example. One building is fine, but if you have a big master plan, using a standalone Autodesk Flow, I will recommend it, and that one instead of using a plugins.
The other question, I understand and I agree it's easier to look at the cost range, you know, but would that be too sensitive if you are going to bring it up to the client? Because you know the cost range, the client will look, oh, okay, that is how much. Then later on, after field construction, then you pay. That is not how much right now. So how you would address that?
Typically, it depends on the project. When we talk with the clients, if there is a liability or it's like a part of the proposal, we usually be careful, really cautious how to present it to the client. Typically, we all want to show it as a percentage of saving compared to the baseline. That's the safe bet. Because if you say like dollar value and after that they run the building, it's not different. It's create a liability issue, and how you will address it. You probably can go through the building and make adjustment on the recalibrate your energy model, but yes, it's true. It's a lot of risk from a liability point of view. So if you have a client that really concerned about that one, probably it's much better. This is a possible range. I usually put a disclaimer in below. This is based on the early energy model, based on the existing information. Actual building might have a different energy usage. It's like your car, right? They use a mileage per gallon, but they put tiny notes that the actual your mileage per gallon probably different. So that's usually my approach.
And if I could just add to that as well, there's a couple of things, different things going on there worth considering is the fact that, first of all, yeah, it is a range, and in order to help us process this and give you one number to guide you, everyone's looking at that mean, but it is actually a range. You'll actually see it as a min and a max. And so, yeah, at that conceptual stage, the reason for saying lighting power density is on a 0.4 to 0.7 type thing is that you don't know for a fact. But not knowing that shouldn't get in the way of you making better decisions or being able to make better decisions about things like shading and materials and other things. And then as you go through the process and manage the information, again, as a team, once again, like for example, it's critical. Owners feel they can hold or try to hold or need to hold engineers and architects responsible for building energy performance, but they need to do their part too. So if they don't operate the building the way it was assumed to be operated, like they go 24/7 as opposed to 9 to 5, that's going to have a big implication. So what we're trying to do with this is actually make it much more transparent about what these key assumptions are and the roles that different people have to play around what it'll take to get to that. Because in reality, as we know through things like measurement and verification, these simulation engines can actually represent reality very, very accurately. The difference is never the computation, it's always the information. And it's managing that uncertainty and recognizing the fact that you don't necessarily know precisely what these things are. Because again, that's where, unfortunately, a lot of energy modeling workflows have traditionally started at, give me a detailed design, give me rooms, tell me how many people are in there, from what hours of operation, and it's very precise. And again, that's fine for a rating performance, but in terms of representing what the real building energy might be, it's a different conversation. So yeah, we're trying to actually overcome that.
And a question to you on InSite. Is there a reporting mechanism, or are we just using print PDF?
So yeah, we get asked that a lot, and you can just print PDF. But in fact, we actually would like people. This is one of these things of in technology development of is that a faster horse? Is that or are we? Is there something else at play there? The unfortunate things with PDFs, and I know it's sort of a habit people have, but it becomes a static report then, and it becomes what we actually want to be the thing that's shared is the thing itself, the actual information, because it lets it show that it's dynamic, and you can play with these things and you can understand that cause and effect yourself. It's sort of hard to break that. It's not like you've gone deep into the model somewhere and changed something. It's very easy for someone to save the state and put it back, and you can let people play with it themselves. I mean, if you go down to the exhibit hall, Andy has it on his iPad, and you're just able to say, oh, I can understand what these cause and effects are. So yeah, right now, screenshots, PDF, those kinds of things, but what we'd really like to have is people actually share the thing, which is one of the reasons why we put it in a web browser. So it's not siloed on someone's desktop in the corner of the office. Everybody can have it.
I have a question about shading design, and it's twofold really. Already, you showed a slide earlier on, and you had like a design workflow, and envelope optimization. A little later, it had shading design. I just wonder why they weren't a little bit closer together. And then for Ian, I suppose it around shading design also. What are the inputs within InSite on that?
Yeah. My process, typically when we do a shading strategy, typically we go slightly in a further process. We usually assess the solar first before we apply the shading. So it can be really closer, but that's kind of workflow. You can adjust based on the type of building. We actually have, for each our practice, we develop different type for helping the architect to visualize what they need to do. Because when the first time I came to them, without and try to explain with the word, and they're like, oh, what do you want to explain? So we developed that kind of workflow for each building. Sometimes like interior design only. For like retail, we do a lot of retail. We don't do a lot of envelope optimization. We do directly to interior design. So kind of stuff. Yes, it can be go closer or go further, depending on the type of building, on the type of your project. And what is your concept also? Sometimes architects want a sleek look. That's the trend that architects still want a sleek look. But I think there is a trend now, people start applying more shading device and the shading strategy in early.
And just for my response to that is that there's two sides to that. One is, if you look at those factors at the moment, it is pretty complete, but it's not every possible strategy, and shading is not included in there, but it is relatively easy to conceive of that being in there and part of the configurability of it. But for the moment, it's relatively easily done between Format and Revit. In part of that energy model, translation is able to recognize when something is room bounding and when it is part of the heat transfer simulation of the building, or when it's a physical shade that sticks outside the building. In those examples there, actually, I have some of that in there. But and basically that becomes part of the GBXML type shade, and then so you could very easily create design options around that. But right now, we're not parametrically varying it, is the sort of short answer. But as I said, it's relatively easy to do in Format or Revit, and there's possibilities to do that in the future.
A little bit more technical question. So let's say after the early design stage, we move on to, let's say, a little bit more. We realize that the window to boring, so we realize what is the best. So architects start putting up the sunshade. We're trying to reduce the heat gain from there. Does the engine help to calculate the thermal bridging as well, because that is going to affect the overall U factor of energy?
I think for the I think if you go slightly further, I think in my process, I typically go to another software. That's using the capability of InSite, you can actually export it, the GPXML file that you can bring to another type of software that probably can give you more detailed input, like more depending how far you are in DD. You want really detailed, probably start inputting CFM and kind of detail. You probably want to export if that's the approach that you want to do. So that's my recommendation.
I personally run into a lot of questions like that. Architects come to us, hey Joe, what about the thermal bridging? We're concerning about that. So that's why I just want to bring it up.
Yeah, thermal bridging, we usually, because we are architecture firm, I think we also advise our architects to do a thermal bridging study. We usually use term. It's a free stuff. That's the one that after that, you need to more robust energy modeling, probably more detailed energy modeling software.
And again, the only way to really account for thermal bridging in a whole building energy simulation, because it is 2D polygonal geometry, is to account for that thermal bridging effect in the overall U-value properties, which is what you use term to kind of calculate. So again, at that conceptual level, when you're sort of broad ranging things, when you get beyond that, and again, remember, all we asked to get started was some geometry and location. But when you start getting to the point where you're now picking a curtain wall or picking wall properties, and that all that information can be embedded in Revit. That's been around for quite a long time. It's a little bit buried, and it's part of the Revit materials and so on. But again, we have that workflow pretty well documented. But you can set the thermal properties. So if you calculate what the thermal bridging effects in Therm are, or you know how to account for them, that can be encompassed in the building element thermal properties and in the curtain panels and things like that. Yeah, so you can actually feed it into the Revit model, and the next time you run the analysis, that actually gets used in that, yeah. And what you'll see is the relative difference in that range.
Yes.
Stephanie was showing me this on the expo floor, and I noticed when I added PV to the project, it provided a cost for that PV system. Are any of those other parameters tied to a capital cost?
Yeah.
Or relative capital cost?
Right. So right now, no, not the others. What's unique about PV is that the first costs of PV relative to things like efficiency and so are relatively well known. So as part of that running cost saving, we can actually do a life cycle calculation to see what that actual net effect is. But of course, glazing costs, HVAC system costs is much more complex. Again, there's a couple of problems here. The first one that's always been hard to get is sort of reliable information on potential running costs. Given that, you know, a design team or an experienced architect and engineer can sort of bring that other piece of information about what these other options can be and do those return on investment calculations. But again, that's another thing we can sort of look at in the future. But right now, no, the factors are literally it's just running cost, and everything else. PV is unique that way. And that's why on the PV factor you see a payback period factor as well as the efficiency factor.
Yes.
So as you, I guess, progress farther along the design, are you actually able to, using this program, input more precise values in a sense to almost override its assumptions with your calculated, say you calculated in a third-party program?
Mm-hmm.
Are you able to input those variables, or say, you know, your cost of glazing? Can you actually start inputting that and to kind of use that same platform to track all the way back down through almost the
Yeah, now it depends on what information you're talking about, but that's sort of what we were talking about there relative to at least material thermal properties and glazing, where, you know, at the early stage you go from the ranges to saying this exact curtain wall has these exact properties. You know, you are overriding that behavior, that essentially initial simulation that seeds that range.
But you can do that for all the categories.
So I'll tell you exactly what you can do it for. You can do it for all the material thermal properties, walls, roofs, floors, glazing, windows and curtain walls, and then also using the Revit space objects by placing them in the model and telling them, like, this room has this occupancy, this lighting power density, or even this number of lights. Remember, you know, in Revit you can model lighting systems and you'll get the exact number of lights in that room, schedules of operation. Any additional information that you add to the Revit model starts to get added to the equation. So again, we talk about this going from the generic to the specific, or from options to decisions, and it becomes a very conscious thing. What you can't do, and which is no secret, is that you can't get into the detailed HVAC system side of things. You can't go in and start picking different pump curves and configuring things in different ways. The HVAC system side of things, at the moment, there's a single factor for overall system efficiency, which just helps you understand what the overall opportunity is there. You know, you still, for those kinds of things, you'll still need to you know, use things like eQuest and Design Builder, IES, stuff like that, all that. We're not trying to replace those things. You know, we're trying to actually complement them with a more front-loaded overview of what the building performance is. Does that make sense?
If there is no other question, I think we conclude this.
Is InSite, maybe Stephanie, is this getting into the EPA certificate?
So it isn't today, but we're looking at updating that. I would say look for something maybe in the next 6 months.
So next semester we're still working with it.
Yeah, so for your spring semester, it'll still be, yeah, so it was released 2 weeks ago, and we want to make sure you have good data sets, and you want to make sure that it's not too easy to break the model, so it's going to take a little bit more time to get InSite, but we should have it for fall semester.
Okay, if there is no other question, close it. Thank you so much.
Thank you.